Okay. All right, so I was given the broad rubric today of talking about transport properties. I'm going to give what is largely a mineral physics perspective. I'm going to provide basically sort of an overview of the different flavors of transport properties, which basically boil down to whether you move heat, mass, or electrons around in the planet. And that's what the dimensions that I'm going to assign to transport properties per se. There are going to be ramifications in what I say for the viscosity of the planet, which I'll allude to in passing, but I'm not going to cover the actual viscous behavior of the planet very much at all. So I'm going to basically provide a brief guide to formalisms, talk somewhat about in sequence for each one of these, how they are actually measured. So when you actually look at a paper on something, you can say, all right, well, that looks like a very credible measurement, or looks like that at least people know what they're doing. And then I'm going to give an example or two, hopefully a fairly recent one, of each of these phenomena that is of interest for the deep Earth. Okay, so the thermal conductivity is one of those parameters which has arguably attracted a lot more attention in terms of experimental work, theoretical work over the last decade or so than it has in the past. And the reason for that is it's a rather coarse parameter. It doesn't vary by too much between different materials other than between things like silicates and metals, or fluids for that matter. So the thermal conductivity, the geophysical issues at stake are pretty profound nevertheless. For example, the heat transport or the heat gradient through conductive zones, the lithosphere and D double prime in all likelihood, plus any other conductive zones you want to find within the deep Earth, hinges completely on the value of thermal conductivity. The rate of equilibration of thermal anomalies, things like slabs, how long the slab's thermal signature persists, is critically dependent on thermal conductivity as well. And finally, it's an input to fluid dynamic models. Of course, the thermal conductivity lies in the denominator of the Rayleigh number, so if you want to do a scaled fluid dynamical model, you actually probably want a decent idea of what the thermal conductivity of a material is. So thermal conductivity, there's basically three main transporters of heat within the Earth. In things that we think of as in the mantle, insulators, and I'll loosely extend that to semiconductors, if you have vibrations within the material, thermally driven vibrations, we'll use the term phonons to describe them. That's just a description of how waves, thermally driven waves that are associated with the vibrations of individual atoms within the lattice are propagated through a material. So for example, if I put my hand on this desk, the thermal signal that propagates through the other side is entirely driven by thermal vibrations within the material. It's controlled by the rate at which those thermal vibrations propagate from the surface to the bottom of the table. Okay? So it's a fairly simple concept. Now, the interesting thing about it is that it's not a simple relationship between temperature and thermal conductivity. This is a log plot of a sort of a generic material. It's actually a fluoride. Of thermal conductivity in watts per meter per Kelvin as a function of temperature on a log scale. And at low temperatures, up to something around 100 K or so, and that's true of most materials, you have a proportionality that goes as the cube of temperature. And that's simply because as you increase temperature in a material, you have more mechanisms by which more accessible vibrations in the material that can be used to transport heat. Okay? And that's the same tendency as this actually mirrors very closely what happens with the heat capacity of a material. How much temperature it takes to heat up a material by 1 degree Kelvin actually scales as a T cubed law in this area as well. So it's basically just how much the vibrational field in the sample is what the vibrational field within the sample looks like of oscillating atoms in there. Then you get to a turnover point, and you get a precipitous decrease in the thermal conductivity. And that goes as fairly linearly as 1 over temperature. The reason it goes as 1 over temperature, and the theory for this is not actually very simple, but the rationale there is that it's controlled by basically when you put a thermal pulse into a material, it has to basically, that thermal pulse has a certain directionality associated with it. Let's say if I have my hand on the table, the heat is propagating downward within the table. But there's that ambient field of vibrations within the material. So you've got sort of vibrations that are trying to propagate in one direction, let's say downward in the table after I put my hand on it. And then this ambient field that's around that's doing random things, that's just responding to being at high temperature. And there's scattering that takes place between the vibrations that go in this direction versus the stuff that's just there at random. So as you increase the temperature, what some would call the phonon field, I'll try not to use that word today, the basic environment, there's more stuff going on, and there's actually scattering that takes place. So it's harder for a thermal wave to propagate through a material at high temperatures. And this is really the range of geophysical interest, is in this zone right here. That's fortunately a very simple temperature dependence. Okay, you'll notice I have 3 main transporters up here. And my 3 main transporters, which I will go through in the next 2 slides, you anticipate me, are respectively our illustrious phonons. Oh, I used that word again. I'm sorry. Our lattice vibrations, electrons, and photons. Okay, those are going to be my 3 transporters, which is fairly comprehensive.
Right.
Yes?
High temperatures as you approach the melting temperature, there's a deviation from 1 over time.
Yeah, that's true. Yep, that's true. And I will allude. That's right. You are correct. And you anticipate a certain amount of this talk as well with that question, which is that, in effect, as you get closer to the melting point, you also get additional defects taking place that occur within the lattice as you get close to the melting point. And so it isn't strictly, so in this range, which is a lot of geophysics in this range, in terms of being in a proportional to T regime, it is controlled largely by, and certainly the ultimate location of where this point lines up is determined by the trajectory of the 1 over T dependence. But yeah, it depends on, if you're propagating a thermal wave through the lattice, it depends on all the scatterers that are present within it. So defects will have some effect, impurities will have some effect, and it has near the melting point, that the deviation in this instance is reasonably small, but you wind up getting some interaction with defects as well that occur near the melting point.
Show us where rock plots at 300K.
Rock would plot about right there at 300K. Okay? So somewhere in there, actually probably over in here. This is a relatively high thermal conductivity material. This is just to illustrate the temperature dependence of the whole thing.
So a rock would plot?
It would plot somewhere. Yeah, it would plot somewhere down here, but parallel on this curve. Okay? Okay. If we look at another mechanism, this is the temperature dependence of the thermal conductivity of iron as you heat it up. This is a fairly complicated material, actually, in a lot of ways, and also obvious geophysical importance. So in this instance, as you heat this stuff up, you get a characteristic, more or less 1 over T drop off in it. But the thing with iron and other metals is that you have both lattice and electron-mediated thermal transport. And later on in the talk, I'll show the relative partitioning between how much heat is carried by electrons versus how much is carried by vibrations. And the nice thing about this is that they both are dependent on scattering processes. They're both interfered with by stuff that makes the lattice irregular, whether it's lattice vibrations, defects, phenomena that would impede the propagation of a nice clean wave through a crystal. Anything that messes up the nice ordering of a crystal, whether it's atoms bouncing around, or whether it's an atom plucked out as a defect. Those are all things that will ultimately interfere with the propagation of thermal waves through a material. So you can see a nice drop off here. There's a phase transition a little over 1,000 K in iron from body-centered cubic to face-centered cubic. This is at ambient temperatures, or ambient pressure, sorry, it's at high temperatures. There's actually probably, relevant to Michael's question, in the FCC phase, there's probably a large component of defect generation that occurs at the phase transition and subsequent annealing that produces this odd temperature dependence. And then the liquid winds up having a dependence which is loosely positive, and it is probably in this temperature range, has a large input from basically ionic conductivity as well, just heat being moved by atoms themselves. So it's not a simple pattern, but the key thing that I would point out here is that this is not a very coarse scale here. This is 0.1 watts per centimeter per K to 1 watt per centimeter per K. So this is only varying by factors of 2 and 3 across really a very dramatic sequence of structural changes. This stuff has gone through a major structural transition from two types of packing, from one type of packing to another, and ultimately melted, and it actually hasn't changed by all that much. So it's actually sort of so in terms of the temperature dependence, it's somewhat insensitive for metals, I would argue. And especially when you look at the formalism, which we will in a couple slides, that this is basically where this feeds into geophysical problems is as the square root of the thermal conductivity. This becomes a fairly small effect, except for a few instances. Finally, thermal conductivity via photons, where basically you have emission of photons, and this is one of the more complicated figures I'll show today, is something which occurs in the literature. Every 15 or 20 years, somebody says, thermal conductivity via radiative conductivity is vitally important for the deep Earth. It runs in a very nice cycle and has since about 1958. We're in about, I think we're about 4 years since someone last said that radiative conductivity was critically important for the deep Earth. The dilemma with energy propagation by phonons in the Earth is that, unfortunately, the Earth is colored. And it's actually a very delicate and fragile phenomena, the transparency of materials. So what this relies on is the standard emission curves of materials. Stuff sits at high temperature, let's say 2000 K, and these are the standard Planck emission curves for radiation as a function of wavelength. This is actually the visible range in here, infrared over here. The peak, as you all know, moves progressively towards the blue as temperature is increased. And so 2000 K is not a bad estimate for a lot of the mantle. You wind up with a peak that's somewhere around a couple microns in wavelength for the peak wavelength as a function of intensity as a function of wavelength. Well, a lot of effort has been devoted to determining what the optical properties of minerals are at high pressure and temperature. And the goal of that is to figure out how far a photon can propagate in a mineral. Because if you actually have radiative conductivity, your conductivities go way up. Okay, it's an immensely efficient means of transporting heat. So if, for example, I shine a bright light at you behind a glass, which has a very high radiative conductivity, you're going to feel the heat from it. We all know that. By the same token, if you have a transparent mantle, you can basically imagine a situation where you would just radiate the heat from the core and it would arrive at the base of the lithosphere and everything would be a very different world out there. And unfortunately, what actually happens is that you actually have, and there's a sequence of ugly absorption spectra, which I've labeled in wavelength up here. So this is increasing energy, but the wavelength is up here. So this is 2 microns at 5,000 right here, 1 micron at 10,000, that's over here, and 0.5 microns over here. I'm not going to belabor the details of this too much, except to say that what you have here is you have a spectrum of post-Perovskite at 140 GPa, you have a spectrum of Perovskite at 133 GPa, spectrum of Perovskite at 133 GPa, and you have a spectrum of MgFeO. I got these, it's 140 GPa post-Perovskite here, MgFeO here, Periclase at 36 GPa, 133 GPa Perovskite down here. Sorry about that. And the key thing about this is that to get radiative conductivity to work, you really need a value on this scale of something on the order of 10, 20, something on that order. This is a unit of absorption coefficient. It's essentially a measure of how far a photon can get before it is reabsorbed. Because if you emit a photon, and photons are emitted thermally all the time, but if they immediately get reabsorbed in the material, you haven't moved any heat at all. Because you generate a photon, radiates, gets reabsorbed, it has to re-radiate in its first perfectly spherical way, and then it gets picked up, and you haven't moved heat at all. So if this number is even in the tens, you wind up getting zero radiative conductivity, or extremely little. So the dilemma here is that there's also a dirty secret of mineral physics as well, which is mineral physicists tend to do experiments for very good reasons on relatively simple systems. This is a pure Mg.8 Fe.2. There's lots of transition metals in the planet at the 100 ppm level. everybody knows, well, not everybody knows perhaps, but if you look at a ruby, a nice ruby, your average nice ruby has about 400 ppm. Okay, a nice ruby. I can't vouch for what his chromium content is. Never mind. We're not going there. But circa a nice ruby has 400 ppm of chromium in it. I don't know what a mean ruby has. And that gives it a very deep, nice red color. And that's the type of coloration that can absorb visible photons very readily. So every transition metal you pick out, whether it's present at the tens or hundreds of ppm level, has its own individual absorption spectrum, which is superimposed on here, some of which are strong. So actually, for this type of conductivity, you actually need to worry about the manganese. You need to worry about the nickel. You need to worry about everything if you are going to claim that radiative conductivity is important.
And if you want to claim it's not important, you have to worry that impurities could lower the absorption coefficient?
That would be one implication, yeah. So it is rather, well, let's put it this way. You would have to make a firm statement, you would have to know what the defect concentration is very accurately and know what the integrated spectrum looks like very accurately. And I've only talked about thus far the effects of nice things that just substitute into lattices, like iron, nickel, manganese, magnesium, for example. I haven't included grain boundaries at all in this. And grain boundaries, some of them can be messy. They are not necessarily entirely transparent. And you can get intergranular phases as well.
Don't all those things just add to the absorption?
Yeah. This is the challenge for radiative conductivity, which is why I'm going to present a fairly skeptical view that radiative conductivity has any importance whatsoever in the mantle, even though it does go on a 15-year cycle in the literature. Somebody will come along and say, radiative conductivity. Sure.
Mm-hmm. But if the grain size is, let's say, a millimeter, mm-hmm. It may not have much influence on a meaningfully path, right? The meaningful path of the photon.
Okay, that's why I've belabored just simple iron substitution into the lattice in this type of a figure. Because if you have basically your Mg90, Fe10, whatever you want as far as the chemistry of it goes, and I would say Mg89, Fe9, nickel 0.05, and so on down the line, going down the transition metals, those are actually still in the crystal there. They're still sitting there. So that's where I totally want to divorce this discussion from the grain boundaries, unless asked about it, because those will absorb just fine, thank you very much, even on the 1 centimeter scale. You can make the meters a meter. You can make the grains a meter. Make them 10 meters. Make them 100 meters. And you will still get absorption at those frequencies, because it's an intrinsic property of having the transition metals embedded in the lattice. Okay? So one wants to, my general preference, if one has one druthers, is to avoid a discussion of grain size in the mantle. Just a general preference on my part. Yeah. Okay. All right. Yeah. It's between 1 and 10 centimeters. Yeah. Sure. Whatever. Okay. Now I'm going to cover mostly just to remind you of what the nature of the fairly straightforward math that many of you have seen before is for thermal diffusion, because it's identical to the chemical diffusion as well, which is that if you have heat flow per unit area per time, this is classic Fourier's law, you have minus the thermal conductivity times the temperature gradient. And that's a very powerful statement right there. You can describe this as vectors. If you want to describe it in a vector notation, you have Q equals minus K grad T. That's fine. But actually, the correct way to describe it, as it turns out, is actually as a tensor. And effectively, what that means is you have to describe thermal conductivity as a 3x3 matrix. You have to do the same with chemical diffusivity as well, because you have different rates of thermal conductivity in one direction versus another direction versus another direction. So it actually is an anisotropic property. And of course, the classic thing is that if you take it with respect to time, you can do a little energy balance and write an equation that relates the time dependence to the depth dependence. where this is density, that's heat capacity, and change in temperature as a function of time is just thermal conductivity times the second derivative of temperature with respect to distance. And you get the beautiful classic net solution, which has been around forever, literally, which is based on some reference temperature, some surface temperature, that the temperature depends on a delightful parameter called the error function and the square root of kappa T, where kappa is the thermal diffusivity in this instance. And so the error function, 1 minus the error function, looks like this, and the error function looks like this, and they're complementary to one another. And if one turns the standard oceanic geotherm diagram on its side, you see that we intentionally always calculate it, no coincidence here, as an error function distribution of temperature versus depth. And at times we'll put, in continental environments, you can put geothermal and barometric measurements from different minerals and try and fit that to that. But it's a fairly straightforward relation that's just incredibly handy. And it's also a nice way. There are lots of ways to measure thermal conductivity, lots of them. And I don't even claim that this is a comprehensive list. One way, which I'll illustrate in the next slide, is you can modulate the thermal input into a sample and look at the response. So in essence, what you can do is basically put in a sine wave of pulsing into a sample, measure the temperature at different locations in the sample, and invert that for the thermal conductivity. Has been done at Bayreuth. The input, you can put in a thermal pulse, like a laser flash, onto one interface, have it absorbed as a thermal spike, and then look at the rate at which that propagates through by looking at, let's say, the infrared emission, or the emission from the sample at the other side of the sample to get the rate at which a thermal pulse propagates through the sample. That's the technique that's been used predominantly by Ann Hofmeister and others. There's been a few measurements on this at very high pressure done by Goncharov and others that have extended this to fairly high pressure and temperature conditions. So this is actually an area where the measurements are actually extending to a fairly deep depth through the planet. You can do things that, which Abby Kavner and others have done, which is measure and model thermal gradients within spot-heated samples, which go to very high pressures and temperatures. There's very fancy optical techniques, which I won't talk about, which are effectively to set up a vibrational, standing vibrational wave within a sample using lasers, turn off the lasers, and look at how long it takes for that vibrational perturbation to disperse in the sample. And that's called phonon decay. And then, as Razvan talked about yesterday, there's also theory, which is often defect-free solids, which is an important parameter to keep in mind.
There are three mechanisms for heat transport. Are these different methods for measuring it? Sensitive to one or the other, or all of them?
Yeah, actually, they would be. This would be sensitive to all of them. The input thermal pulse would also actually be sensitive to all of them. This would also be sensitive to all of them. This would only be sensitive to the lattice conductivity. Okay. And theory would be largely lattice and electrical conductivity, or lattice and electron-driven thermal conductivity, predominantly. There's typically not radiation included in the theory. Yeah. We'll get to that in a minute. 2 slides. Give me 2 slides and I'll get to that. Yeah, I mean, this is a delicate issue because it depends on which optical technique. And the one that has been most commonly used, which is impulsive stimulated scattering, is a raw phonon decay. So yes, there are optical techniques which can prospectively sample radiative conductivity, although they are actually less commonly used than impulsive stimulated scattering. So this is actually one of the sort of classic experiments, I would say, at this stage in measuring thermal conductivity at high pressure and temperature. What this is a cross-section through a sample. It's got a thermocouple right here, a thermocouple at the center. It's got a heater on the outside, and the voltage or current to the heater is modulated. It's modulated in a sine function, at a designate frequency. So a relatively low frequency here, a relatively high frequency here. So you have an inner thermocouple, an outer thermocouple, and there's a phase lag between the two of them. And from that phase lag, which is highly frequency dependent, you can actually invert very accurately for the thermal conductivity of the sample. It's actually a very robust technique. And so the net results from this are summarized here in terms of the thermal conductivity of in this instance, olivine at high pressures and at both high pressures and high temperatures. And what you can see is that there's a loose pressure dependence that is fairly small, actually. Turns out that, and I'll mention this in a couple slides, that it scales loosely as 1 over volume to the one-third power. So as you increase the density, the thermal conductivity goes up by a little bit. Polymorphism does have a very significant effect, which is that depending on the phase, and the way I would look at this loosely is I would look at this as phases of diminishing structural complexity going this way. The highest thermal conductivity here is a spinel structure, which is actually a pretty simple structure. Olivine's a more complicated structure. Wadsleyite is intermediate between those two. And the reason that there is a distant correlation here in some way that with structural complexity is you can imagine that the vibrations are dependent, that the nature of vibrations in the material are dependent on what the complexity of the crystal structure is. So there's a tandem effect of increasing density on the thermal conductivity, but also there's a trend of complexity as well, which is basically what the vibrations look like in each material, and they're simpler in a simpler structure.
So at a given temperature, if we plotted those conductivities against pressure, or against volume, would we see a deviation in the trend owing to the complexity of the structure, or the densification of those different phases not the most?
The breakdown would be you're asking actually a very nuanced question in terms of what is the different role of just bulk density versus what is the spectrum of the material. And I'm not going to give you a percentage because I don't know the percentage off the top of my head. But both play a role in this. And there will be a temperature dependence attached to each one of those. So you will notice that the ringwoodite has a more substantial temperature dependence, even if I scale it to K on K0, let's say. Yeah.
Are there any issues, experimental measurement issues, like gradients across samples or contamination by the
Oh, there are always some level of experimental difficulties. But I would say that this type of experiment, you'll notice that the beauty of this type of experiment in terms of thermal gradients across the sample is, and I probably should have pointed this out, is that the temperature variation here is actually very small. It's 4 degrees Kelvin across this entire thing. So you have basically the sample at a high temperature, and then you are basically modulating the temperature by just a few degrees. So temperature gradients are a much smaller problem in this instance. Contamination is something that experimentalists worry about endlessly. That's what we do. This is a very actually clean experimental assemblage, I would view this as. I mean, you could say, well, what about the grain boundaries that are clearly present in this material? And yet, they will have some effect. But at least the general geometry of this is designed to minimize, sort of the general experimental uncertainties. And those grain boundaries are not going to change over this pressure range over the time frame of this experiment. So you're looking at basically any effective grain boundaries that are imposed on this are going to be identical across all of these temperatures. So it actually is a very good relative measurement of what the temperature dependence is and how much the magnitude of the thermal conductivity changes by. So there are certainly other experiments on that list that I showed that are dirtier experiments. No question about it. This I would regard as an extremely clean experiment. Yeah.
One potential problem is that the theory is valid for an infinitely long cylindrical sample.
That's true, and you can do numerical simulation. You're right. I mean, so you're correct that this is, but actually, these authors actually didn't do a detailed numerical simulation of that. But the correction is not that large because this is basically let's see, we've got basically 400 microns between these, 800 microns, almost a millimeter between these thermocouples. Sample's probably 5 millimeters long. Yeah, there are probably going to be some edge effects, but probably not too invasive. I don't think they negate the measurement, but that's a good point. I know you are. Yes, yes, I know. And you didn't do a simulation of that, did you? Bad boy. That's not a nice ruby. Okay.
Curious oscillation almost looks like systematic in the Lockley data. Does my eye like this?
Good question. Dave, why is there that systematic oscillation? Darn it. What'd you do wrong there? I would say that, I'll answer for Dave. I don't mean to put you on the spot. That I don't know in detail what actually might have gone on there, but what I would say is that these experiments are not easy experiments to do. And that the net trajectory, you get a little scatter in different runs. Maybe there's a little bit of difference in the detailed geometry of the sample that isn't fully corrected for, and you get a little deviation that pops out. But I don't think that it's something that obviates the measurement. And actually, I don't know if these were done in different runs or not. Don't recall that. They're the same ones? Okay. So what'd you do wrong? Come on. Okay. All right. It's good to have the author in the audience. Okay. Now, going back to the question earlier about thermal conductivity being a tensor. There actually has not been an enormous amount of work done on thermal conductivity of single crystals. But there has been some. And this is to, little inset is to remind you of the olivine structure. The 100 direction is in this direction right here. That's the seismically fast direction, the thing that produces anisotropy of the suboceanic lithosphere. Fast direction this way. And what you can see is that for at both ambient temperature and at high pressures, there is a significant difference of order a factor of 70% or so, a factor of 1.7, between the 100 direction and the 010 direction. So if you actually do align olivine within the Earth, and you clearly do, that would imply that the thermal conductivity would be prospectively variable by, alignment is not perfect, so 20 or 30% potential anisotropy of thermal conductivity within the planet, depending on the degree of anisotropy of materials. And that anisotropy, of course, persists at high pressure as well here. This is an example of thermal conductivity as a function of temperature from Osako et al. And you can see that the difference nicely persists to high pressures and temperatures. So the aspect here is that this could be for anisotropic phases, and I would simply point out that post-Perovskite is a very anisotropic phase, that this could actually be a relatively important effect relative to the effects of things like mineralogy, pressure, and temperature. If you look at the magnitude of change here, this is a fairly decently respectable change in thermal conductivity, depending simply on the crystal orientation of the olivine present in this material. And the pressure dependence, sort of spans this approximate range as well. So, pressure, anisotropy are more or less could be equal contributors to the thermal conductivity of materials within the planet. Temperature is a bit larger effect, but hopefully we know temperature better. Yes?
So, given that I don't expect the mantle full perfectly aligned.
Oh, no.
Crystal, can I pack that down to 10% of that?
Yeah, or 20%. I would say 30%. 20, well, depending on what area you're looking at. Use your surface wave observations, Ed. Figure out what the anisotropy is. You tell me what the anisotropy is. You can break it down then. Could be as high as 30%, I'd say, depending on what you want to make the anisotropy. Okay? So this is something where the seismologist can tell other people and then can tell, Yeah, as it should be. Right. Sure. Talk to me, Ed. You need to talk to me more.
Yeah, but it does seem that it would make much of a difference if you take both, if both the mantle or
I think geodynamicists would not care so much. The people where it would have more of an impact is in terms of rate of equilibration of slabs. I mean, do recall that the uncertainty in rate of equilibration of slabs is largely not largely in thermal conductivity, but in terms of the amount of shear heating that takes place at the surface of slabs. So that's actually the big uncertainty. But one of the points here too is that, remember, all of this enters in as the square root of this parameter into thermal conductivity calculations. So, okay, if you want to do plus or minus 10%, you probably want to know this pretty well. If you want to do plus or minus 40% in terms of times of equilibration, which is usually often good enough for thermal equilibration, you're probably okay using a value of, let's pick a value here, of if you had a 293K something, 6, 7. So it isn't a parameter which is on which you live and die. Let me put it that way. But nevertheless, certainly there have been there are perspective. It's important to be aware that if someone says that the thermal conductivity of olivine at some point in the Earth is 5.2, probably not 5.2. Probably has a pretty decent error bar on it, and you do see that fairly frequently. Okay, so if you actually have the motivation, the will, the desire to extrapolate thermal conductivity to high pressure and temperature, it's not that hard to do, actually, other than the anisotropy. You probably don't want to look at the detailed theory if you're not a mineral physicist of how to extrapolate thermal conductivity. But the temperature and pressure dependence of the thermal conductivity of pure phase depends on basically 1 over the length, we'll call it, or 1 over the volume cubed. Or 1 over volume to the 1/3 power, 1 over the cube root of volume. Oh, there's that phonon word again. The shift of a weighting of the phonon spectrum with pressure and temperature. Suffice to say, how the lattice vibrations change as a function of pressure and temperature. That's all this fancy verbiage means, which goes back to Mark's earlier question. And the really uncertain thing is how much does scattering change as a function of pressure and temperature between lattice vibrations, and that's not at all well constrained. You can look up Ann Hoffmeister's paper from 1999. Also look at the correction too, because some of the equations are corrected in a later version. It gives long formulas for this, very long formulas for extrapolating thermal conductivity. Realistically, there's a couple of gross and not too bad extrapolations out there. One of which is used by Dave Chapman, which he basically plotted a bunch of data, said thermal conductivity is proportional 1 over T to a power that's close to 1, times 1 plus the pressure derivative of the bulk modulus divided by the bulk modulus times pressure. It actually works pretty well. Correspondingly, Mantha-Lake and co-workers came up with this expression which has the same temperature dependence and a little more complicated density dependence. There's a bunch of thermodynamic parameters here, Gruneisen parameter, its derivative with respect to volume, the pressure derivative of the bulk modulus minus a magic factor of 4/3. It's basically a thermodynamic derivation. The key thing here is if you really want to know thermal conductivity, you can plug in some numbers and get it out. But do worry that it might be anisotropic. It works to some degree, let me put it that way. What I would say is that the bulk sound speed does not necessarily scale as 1 over temperature. Yeah. Oh, okay, the pressure, you're asking about the pressure dependence. Okay, all right. Yeah, the pressure dependence, it loosely, you could argue that it should scale roughly, give or take a little bit. Yeah, you make me uncomfortable because in detail, the sound velocity hinges on acoustic phonons, and the scattering has both acoustic and optic phonons in it. So I'm personally a little uncomfortable, but it's probably not a horrible approximation. Mm-hmm. What I would say is that, what I would say is that to the degree that optical phonons behave as acoustic phonons do, that would be the way I would phrase that statement. is that if the optical phonons behave as the acoustic phonons do, then you can model it as being primarily dependent on acoustic phonons in the sense that the optical phonons behave as the acoustic phonons. Sorry guys, sorry geochemists, sorry seismologists, we apologize. But so I'm a little reluctant on that one. Okay, let's move to chemical transport. All right. The geophysical issues at stake include, with chemical transport, include obviously the ultimate homogenization of geochemical heterogeneities. If, convection is a wonderful thing, it can thin heterogeneities down, but if you are actually melting mantle and things like that, even if you have tendrils of material present, you may preferentially sample those tendrils of material, eclogitic material or whatever, during the melting process. So the ultimate homogenization of heterogeneities, and what I mean by homogenization is that they are basically chemically erased, and what you look at is a homogeneous matrix of pyrrolite as opposed to Harzburgite plus eclogite. That's ultimately controlled by diffusive phenomena. This also exercises a control on viscous flow. Diffusion creep entirely hinges on the rate at which mass can be transported by diffusion. And there's a relationship I'll show in a little bit on that. And there's also a direct feed through to electrical conductivity through ionic transport. Okay, I have to show some of my own data here, but it's old. So chemical diffusion is really conceptually a straightforward measurement. You basically take a chunk of chemically different material or isotopically different material, whether it's bulk material, two crystals juxtaposed, depositing a thin film of something else on a surface, depositing an isotopically anomalous surface layer on something else. You cook it pressure and temperature, you slice it open, you look at it and you invert, and you look for the variation in chemistry across the sample. Conceptually, about as easy as you can get. In practice, it's not that easy. So this is a picture of mole fraction nickel silicate across the magnesium silicate. Pure Mg is right here, pure magnesium, pure nickel up here. So we can talk about iron in a minute. And what you have here is basically a cross-section across the magnesium-nickel joint across the phase diagram at about 13 GPa, where you have olivine, beta phase, gamma phase, and this is the diffusion profile across this whole thing that you wind up with after you cook it for 48 hours at about 1900 Kelvin. And you can see that you could invert this type of curve, that type of curve, maybe even this tail right here if it were a little longer, to get diffusion coefficients out of this. There's a little equation here, which the only thing I would emphasize about it, these are concentrations at way out here, positive infinity, concentration at negative infinity, way out here, so 1 and 0 in this instance. And then there's the error function here, which is the same error function, 1 minus the error function that we looked at for thermal diffusivity. And this is, of course, the diffusion, the chemical diffusivity right here. And the nice thing about this is you can get concentration dependence of this, and there's an unusual richness of this for multi-phase assemblages. You can get out, constrain the phase diagram of this material from where this discontinuity occurs between alpha and beta phase. You can even get partition coefficients from the relative difference here. There's a lot of potential richness here. Fortunately, you're looking across this is a relatively fast diffusing system by geologic standards, and you're really looking across 30, 40 microns, which makes things a little challenging. And there's been a large amount of work on characterizing chemical diffusion at high pressures and temperatures within the mineral physics community over the last 15 years or so. And the one thing that is sort of the truism about chemical diffusion is you can imagine that if you have a chemical compound, MgSiO3, let's take MgSiO3. It's got a divalent cation, Mg2+, silicon 4+, oxygen 2- in it. You'd think those would move at different rates. Actually, what it looks like is, and this is data that are isotopically doped samples. So you have basically 25 magnesium put in instead of 24 magnesium, 29 silicon instead of 28 silicon in these samples. And this is in silicate perovskite. And what you get for this, and I'll focus on either one of these, is that if you sit and you let this cook for a little while for a day And keep in mind, this is cooking for a day at 1770 K, 25 GPa, and you're getting 200 nanometers of diffusion. Okay, that's a slow diffusion rate. That's a nasty measurement, and there's a lot of credit due to these folks for actually measuring this and doing it with isotopes and getting it right. The remarkable thing about this is that, from this work, that silicon and magnesium move at the same rate. That's a really weird result. And it's a weird result because you loosely expect a 4+ cation to be bound tighter than a 2+ cation. That's the simplest possible chemical bonding in this world. And yet they seem to be moving at the same rate. Well, this is where diffusion gets very messy, very complicated, very quickly. So what's shown here is the type of picture that you need to develop for a scenario that might result in silicon and magnesium moving at the same rate in perovskite, which is what's shown here is vacancies, defects, and atoms. And in sequence, you have an oxygen atom diffusing into a vacancy, leaving behind a vacancy over here. That's step 1 right here. Oxygen jumps over here. Doesn't look like a long jump. That looks like an easy diffusive process. Then your silicon has no oxygen in between it, and this vacant spot jumps across here. This oxygen does the same jump that this one did a minute ago, jumps over here. And then finally, this window through which this magnesium has to jump is now a little bit open. So if you imagine that this magnesium has to jump to this site to diffuse, you want to open this window right here a little bit. And if you create a vacancy right here, via this jump right here, this magnesium can jump over. Ugh! This is awful. This is terrible. I mean, it does explain this data, which is great. But on the flip side, what this requires is a whole vacancy chemistry within the sample to make this stuff diffuse. And so already you're seeing that we're going to have to have some detailed knowledge of the defect structure of materials like this to really understand the diffusion and ultimately the viscosity in the diffusive viscous regime. So this is a messy, messy problem. And it's a problem that's very much in progress at the moment. Sure.
Make it a bit more complicated. Will that a bunch of trace elements?
Oh, please don't. Did you have to? Yeah, sure.
Would that not simplify things?
Well, actually, the thing that would simplify things the most would not be calcium. It would actually be trivalent iron. Because trivalent iron would in turn generate vacancies galore in the sample because it would not be necessarily a charge balance substitution. So I would actually prefer not to have an isovalent substitution. I would prefer to have a non-isovalent substitution. By all means, stick aluminum in here, put trivalent iron in here. But this is a sample. These were done without aluminum or trivalent iron. But that raises... Could potentially. But then you get into a very messy regime at that juncture, which is then you have to know with some precision what the coupling is between the aluminum content, the trivalent iron content, and the defect chemistry is of the sample to figure out what the ultimate diffusion rates are. Okay, so hydrogen is a mobile species. Everyone agrees on that. And the question would be, what would be the degree to which you could generate a coupled substitution of hydrogen with something else? And now that's not an isovalent substitution which doesn't fully charge compensate for any of these diffusing species. So, hydrogen could play a role, so there has been a considerable amount of effort to try and make samples as quote-unquote dry as possible. There's a lot of effort that's devoted to that. But that raises the corollary question as well of how much hydrogen content is there in the mantle also. And so that is an issue as well. Basically, the key question is, what is the overarching sort of minor element concentrations that could impact the diffusive process within Earth's mantle? And that's a very good question. I don't pretend to know what the hydrogen content that substitutes nicely into perovskite is. I would guess that if there's a high pressure hydrous phase that's sitting nearby, it's probably very low. That would be a logical guess. But if it's been exposed to melting, probably very low as well. But that's just a guess.
They show
Yeah. Right. I mean, this is. I did not want to show a 6-step. Wasn't 4-step enough for you seismologists? Yes.
For example, there's also a study of iron magnesium interference, which is similar.
Yeah. And actually, I will show a little bit of data from that in, I think, 2 slides. So, okay. Yeah, 2 slides. So, just to remind you of what's going on here, chemical diffusion is actually, if you know the defect chemistry and you know the oxygen fugacity, it's actually pretty simple to extrapolate in pressure and temperature. It's an exponential function. There's an activation energy and activation volume. It is pretty simple extrapolative means. This is very venerable for simple systems. For semiconductors, this works fabulously. What this activation energy simply is that you're moving something to somewhere else, and it takes some activation energy barrier to get from one place to another. Now, the key part is, and this is the thing that we've been talking about for the last 5 minutes, is that this doesn't include pressure, temperature, or oxygen fugacity variations in defect chemistry that could almost certainly shift diffusion rates. Okay, so diffusion's hard. It's complicated. The one sort of, I won't say saving grace in this, and this is the penultimate figure, I think, or penultimate figure of one FEMG study, is that diffusion is a pretty lousy way of getting rid of heterogeneities. That is, diffusion in most silicates is really slow. You saw that in the Perovskite with a 200, 300 nanometer diffusion profile over 24 hours. There's 2 figures here, one of which is basically a coupled convective stirring and diffusion model for, in different phases, what the length scale of heterogeneities is that you can erase, that my ex-student Dan Farber and I did a long time ago. That in olivine, something around, give or take 10 centimeters, maybe you can erase a heterogeneity. Spinel, maybe it's more like a meter, something like that. Over a few 100 million years. The key part of this is that what erasing a heterogeneity completely depends on, is convective stirring, really smearing stuff out to an incredibly fine scale. So basically just stretching stuff out to a ridiculously fine scale. I mean, you do see that in some peridotite massifs. You do see little blebs of eclogite in there that look like they want to go away at some point if you cook it long enough. So, it isn't crazy that if you have a 3 billion year old slab or a 3 billion year old chunk of commodiotic crust on a slab that maybe it's this wide at this point. It's not insane. And it's that length scale that you need, literally the presenter length scale, this big, to basically get the stuff erased diffusively. That's sort of the length frame that you need. This is for FEMG diffusion in Perovskite. And this is what the scale length is over which you can erase chemical heterogeneities in the sort of 100 million year time scale, the 4.5 billion year time frame. Pick your favorite time frame for how long you want a geochemical heterogeneity to exist, and you get something that is, for anything less than the age of the Earth, well less than a meter, probably of order centimeters at best. So that's kind of so if you want to get rid of a heterogeneity, you're going to have to rely on convection to get it tiny. That's sort of the take-home message of that. Real tiny.
Some of the people in the audience care about geochronology.
Yeah, I know. Yeah. No, I mean, it's not that that's a bad length scale. I'm not being pejorative about that length scale. But suffice to say that you'll really want to get it to that length scale before you get rid of stuff. And, diffusion is not a fast actor. I mean, there's lots of other ways to kill heterogeneities. I mean, you can melt them out. You can percolate a fluid through them. That's a much more efficient means. I mean, one would rather sooner go there than rely on solid-state diffusion. That would be my take-home message on that. Please do some geochemistry. Don't do diffusion, solid-state diffusion. That would be my take. Okay. Something which I'll return to. Oh, that didn't come out of the screen, right? Okay. So the one thing is that the right chemical diffusion rate can also yield viscosity in a diffusional creep regime. That's Nabarro-Herring creep, where viscosity is equal to stress over strain rate. And that's equal to the grain size squared, which is an interesting dependence, times Boltzmann's constant times temperature, divided by a geometric constant times the self-diffusivity and an atomic volume in here. What is this all about? What this means is that if you squeeze on something, let's say a grain, let's call this a grain, you put a differential stress on it, you'll get a net flux of vacancies along these arrow trajectories, a net flux of atoms this way, so vacancy atom interchange. And after you look at after a while, eventually this cube will have elongated. You'll stretched it out entirely by the virtue of having fluxed vacancies in one direction and atoms in another. Well, how about those defects? Okay. This is one of probably the most nightmarish figures I've seen in a while. Because what this is the log of chemical diffusivity versus pressure. Some experimental data primarily from Jim Van Orman's group up here. And what this is at the top is magnesium-wustite, MgFeO. And what's shown is the dependence of diffusivity on vacancy concentration. How do you get 7% vacancies in MgO at high pressures? You put in a lot of chromium 3+ in it. So you create a lot of vacancies in it. But when you change the vacancy concentration, even by a little, 20 ppm to 100 ppm, your diffusivity changes by an order of magnitude. When you change it to very large amounts, it goes up by 3 orders of magnitude. And if you look at the corresponding relations, and this is plotted in terms of 1 over temperature, so temperature is increasing to the left here. This is the diffusion rates for both MgFeO and Perovskite, with MgFeO down here, silicon and Perovskite right here, and oxygen and Perovskite up here. And you see that in this simulation, and this is a simulation with data plotted on the simulation. So the bands are theoretical simulations. The data points are from experiments. Is that you can get a loosely 5-6 order of magnitude variation in conductivity or in diffusivity, depending on your vacancy concentration. Now, the one phase that is particularly villainous in terms of its anisotropy is the post-Perovskite phase. Let's look for a second. This is a post-Perovskite structure right here. And this is the b-axis along here, which corresponds to 010. And if you just look at this structure, you can imagine that, let's say we had a vacancy right here. Moving a magnesium across this sheet of silicon, a silica polyhedra right here is going to be awfully tough. It's got a barrier in there. Okay? So you've got a barrier sitting in there to diffusion in this direction. Whereas swapping it in this direction, let's say in the AC direction, not so hard. You can jump to here, that's a short jump. Jump to here, that's a longer jump. So your chemical diffusion in this material is going to be very anisotropic. So, and this is a calculation done by the University College London group, Aman and others. And they calculate values for periclase, for diffusivity, perovskite, isotropic rate for oxygen. But then they calculate directional diffusion rates within post-perovskite. And what you can see is that the magnesium diffusion rates and silicon diffusion rates in post-perovskite, silicon jumping from here to here, in this direction are extremely slow, 10 to the minus 20 meters squared per second, whereas in other directions, magnesium along the a-axis, which is more or less like this, is much faster. So there's basically a span down here. So this is pressure, post-perovskite stability field down here. The calculated span in diffusion rates is 10 orders of magnitude here along different directions in this structure. Well, these authors then made a rather notable jump, which is a very provocative jump, which is they then said, let's assume diffusion creep predominates. Well, if diffusion creep predominates, then your O1O is extremely stiff. Extremely stiff. Like, this is like lithospheric viscosities in the B direction here if it's diffusion creep. And the 1OO direction is pretty squishy. It's very squishy. So this is this has a quasi-momentous conclusion that if this stuff is anisotropic and anisotropically oriented, you can get some very, very anisotropic viscosities present at depth. My own gut level take on this is that if you have a viscosity this high, some other mechanism, dislocation mechanisms, will intervene and will tend to lower this viscosity. But nevertheless, if diffusional viscous flow dominates in this regime, there almost certainly will still be a major anisotropy in the viscosity of this material.
Quentin, you said this was a calculation.
Mm-hmm.
So what is it they do about temperature?
Well, because it's a diffusional process, they actually use a dynamical method to simulate the temperature. So they're actually, in something like diffusion, you have to have the temperature in there because you never move if you're at 0 Kelvin. It's a very boring diffusional calculation by any standards. So they have imposed the temperature basically in a dynamical fashion. Okay, so they've put in they've used essentially a molecular dynamics technique. So temperature, to do this type of calculation, temperature must be embedded in there. It's not a 0K calculation. Jackie? Oh yeah, I agree. Mm-hmm. Let me think about that for a minute. That's an interesting question. Certainly there are superionic materials that have lithium intercalated within them that have extremely fast diffusion rates in one direction and not in the others. So I can't swear on a stack of Bibles that it's 10 orders of magnitude off the top of my head. I don't carry that bit of trivia in my mind. But there are certainly materials that do have very anisotropic diffusion rates within them. I mean, this is why this is such a startling result. And oh yeah, well yeah, it's in geosciences too. I mean, you can break it this way and you can't easily break it that way. Sure, completely agree. The question would be is the question does come back again to what is the detailed defect structure within these phases. And what I would say in that context is, off the top of my head, there are certainly defects that are present in micas because they are generally impure. And so the question does ultimately come down to is what is the defect chemistry of these materials? Because that would tend to modulate, if you did throw in a lot of defects into the structure, that would tend to compact this or move these up prospectively. But nevertheless, it's a very startling result. That's why I show it. It's sort of like, wow, really? Okay. But of course, the implications are momentous, which is because post-Perovskite is elastically anisotropic as well. If you basically have a phase loop where you're progressively, this is again from the UCL group, this paper, if you put in a progressively increasing amount of post-Perovskite with preferred orientation isolated in a zone like this, so you're orienting crystals nicely in this zone, then you can actually wind up getting, because it's elastically anisotropic as well as presumably potentially viscously anisotropic, you can wind up getting VP and VSH profiles that look like this, which are actually very similar to those that Alex Hutko and Thornley and others got a few years ago that they attributed to folded slabs near the core mantle boundary. This is very provocative stuff. But what I discuss it primarily to illustrate that the interplay between diffusion and the deeper sciences is perhaps not so great for erasing heterogeneities, but it could be quite profound for the rheology within very high temperature diffusive zones that are dominated by diffusion creep. So that's where one really wants to focus, I suspect, in terms of broader geophysical impact. Okay, so that's momentous conclusions based on that. Okay, I'll close by talking a bit about electrical conductivity. And there's a lot of issues that stem very strongly from electrical conductivity. because there's a relationship, which I'll show in a minute, between electrical conductivity and thermal conductivity. Electrical conductivity has, our knowledge of electrical conductivity fundamentally impacts our understanding of the heat flow out of the core, the age of the inner core, geodynamo operational conditions, and that's all symptomatic of metallic conductivity, which is basically very relatively high conductivity. It obviously has the operative charge carriers, or the free electrons, or nearly free electrons within metals. That's characterized by a negative change in conductivity with respect to temperature. It's also used to identify hydrous and melt-bearing regions via magnetotellurics. That's mostly due to ionic conductivity, which typically has a positive, an increase in electrical conductivity with temperature, because ions get more mobile at high temperatures. And lastly, the electrical conductivity is very important for magnetic field filtering by the mantle. If the mantle were perfectly insulating, we would have a beautiful window into the core surface. The magnetic field at the core surface would simply propagate through 3,000 kilometers of mantle and appear at the surface. But because the mantle has a finite conductivity, there's a certain level of filtering that takes place, especially of high-frequency variations, potential high-frequency variations in the magnetic field. There's also things that Bruce Buffett has worked extensively on, like variations in the length of day that depend on electromagnetic coupling in the mantle. Okay. If you're in an ionic conductivity regime where the electrical charge is being carried by ions, the conductivity and diffusivity are very closely linked by a venerable equation called the Nernst-Einstein equation, which is basically a proportionality between electrical conductivity, diffusion, and some factors related to the charge on the conducting species, their number, and KT. It's great. This is a tremendously valuable equation for basically getting, if you measure conductivity, getting diffusion on the cheap or vice versa. But the problem is that one does have to know all the possible charge carriers, their mobilities and vacancy concentrations to make this useful for rocks and minerals. And that's an immense challenge. Now, just to remind you, and a lot of people don't look too closely at electrical conductivity probes of the deep Earth, but if you look at depth versus conductivity of the planet, it's a pretty coarse probe. This is work that's derived from induced currents and transoceanic cables and things like that. It's difficult work. It's difficult inversions. What you can see is loosely that there's a gross increase between lots and lots of models in conductivity through the bulk of the mantle. Most of them then smooth off, although there is some variability depending on which model one looks at. Smooth off at a relatively high conductivity value for a silicate. And if you look at regional models, you'll notice that there is no real signature of a transition zone in here that I can detect, at least. If you do look at regional North Pacific models, these are sort of the three prominent ones at the moment. And they do have some indication of a substantial jump at around 400 kilometers depth. 670, maybe not. There's something there. Hard to say. So this is actually a really, really pretty gross probe. I don't mean gross. Coarse. Gross is pejorative. But people have made good faith attempts to interpret those North Pacific data in terms of the water content of the slab. They've taken basically data on hydrous wadsleyite, hydrous ringwoodite at high pressure temperature conditions, assumed that looked at the anhydrous conductivity of materials. So the three multiple models for the conductivity under the North Pacific are shown in these three panels in green. A couple of these have discontinuities at 400. And you can loosely see that the black line, which is 0 weight percent, does tend to fall below the observational conductivity profile. And if one is very generous and looks at this carefully, one would say that loosely you get about 0.5 weight percent as the closest match. But so the key point here that I would take away is simply that the electrical conductivity, at least under the North Pacific, is higher than the anhydrous conductivity of a mineral assemblage, of likely mineral assemblage under comparable pressure temperature conditions. There's a lot of things that can generate high conductivity. Temperature anomalies, melt, high conductivity grain boundary phases. Well, there's an extended literature in the shallow upper mantle, if you get any level of graphite on grain boundaries. Oh my God, if you get graphite on grain boundaries, you've got effectively a wire connecting, running through the whole system. And so there is a lot of uncertainty into what a modestly elevated conductivity actually means in the transition zone. There's a lot of uncertainties there. And again, it comes down to, in a great extent, to minor phases in the system. You know, no one's saying there's lots of graphite down there. Well, all it takes is a little, because that stuff, just electrons fly through that stuff.
Those graphs, I've been looking at them for a long time. I always scratch my head about it because they're not completely, they're not determined by some model that allows for whatever variation you like. They impose bins, and they say, well, we might as well put a bin at 4 and 10 kilometers.
I know. Your question is a good one. Is how much is this actually demanded by the data? And right, it could be. This is an option, although the misfit of this model is somewhat higher than these other two models. So to their credit, these folks who do this stuff are very upfront about their misfits and uncertainties. And they're pretty judicious, as they should be, I believe, with what exactly is the best model. And this one seems to minimize the misfit of the system. So yeah, I mean, I'm not going to argue that electrical conductivity is a precise probe. Not going to do that.
But the data, like the data that you showed in the different models previously.
Oh yeah, back here.
Yeah. Those steps are assumed in the model.
Yeah, although they.
Magnitude isn't, but the fact that there are steps there.
Right, but the thing that they do is, to their credit, they do a sequence of basically continuous models, and they look at the relative misfits attached to each one of them. So you're right in the sense that they did say there is something going on at 400, but it does reduce the net misfit of their very, very coarse models. So it's probably not a bad thing. It intuitively makes sense, but you're working with this is one of the hardest data sets I've ever seen that people work with on a routine basis. So the fact that they get anything out of it is a bloody miracle in my mind. Okay? More power to them. Okay, so I'll conclude by talking about metallic conductivity. And there's a venerable relationship here, which you'll encounter in papers on relating thermal conductivity of the core to electrical conductivity of the core, which is called the Wiedemann-Franz law, which has been around since the 1850s, which basically says that this number, which has a value, metals vary by something like 10%, with the exception of a few exceptional metals like bismuth and things like that, is equal to the thermal conductivity divided by the electrical conductivity times temperature. This is a wonderful thing, because if in fact you are pretty sure that the Lorentz number is roughly constant, you can measure the electrical conductivity and get out the thermal conductivity. We're going to return a little bit to thermal conductivity here, because the underpinning basis for this, and this is just from 0 to 300 K, and the trajectory continues on up here. This is actually the conductivity of a steel, very close to iron. This is the conductivity that is produced by the lattice itself, by propagation of thermal waves through the lattice. And this is the amount of thermal conductivity due to electron conduction of heat. So you can see that basically this stuff flattens out at about 100 K-ish, and flattens out and moves to very high temperature at about this level, whereas this keeps going and going and going and going and going. So at high pressure temperature conditions, the story of iron conductivity and metal conductivity is almost entirely electron transport. How do you measure electrical conductivity at very high pressure temperature conditions? You can do it in the diamond cell at certainly high pressure conditions. It's a little more challenging to do it at high temperature conditions. But the work that has been most widely invoked for electrical conductivity of the iron alloys at high pressure is shock data, where essentially you hit a sample with conductivity probes on it with a bullet, a flat bullet, and measure the conductivity as the shock wave propagates through the sample. There's been two primary data sets to date on this, one of which is now a decade old, which is the tan triangles here by B et al., and earlier work from Livermore by Keeler et al. Up here. And the disturbing thing about this data set is, so basically you're looking at the electrical conductivity under shock loading, is that if you look at where these two data sets overlap, there's almost a factor of 2 difference. Maybe 60% here, almost a factor of 2 difference up here. this factor of 2 difference is a nightmare. It's a flipping nightmare. Because if one cares about the thermal conductivity of the core, and some people really, really do, that matters very greatly for propagating from electrical conductivity back into thermal conductivity. Why? Probably the best illustration is from a very recent paper from, again, the UCL more theory-oriented group, Dario Alfe, Gubbins, and persuaded by Pozzo. And what they get, and these are similar to stuff that Razvan discussed late yesterday, they take sequences of temperature through the core, they invert their theoretical model for thermal conductivity and for electrical conductivity. And so each of these curves corresponds to a chosen geotherm through the outer core. And what they get is actually quite large values of the thermal conductivity of iron, order a couple hundred, and thus more compatible with the higher values of electrical conductivity, the older electrical conductivity values. Okay, so you basically have a very thermally conductive metal in the outer core. What does that imply? Well, what that implies is that the conductive transport out of the core is larger, that the amount of heat advected along the adiabat or transported along the adiabat via simple conductivity is substantially larger than expected. The power available for the dynamo is thus less. If you want to form an inner core early, it's much harder. And to keep heat within the core, you might need to have stable stratification at the top of the outer core. So based on this curve, or these sets of curves right here, momentous conclusions. That's the one way I would describe it. Now, what are the possible uncertainties here? One is, we'll discuss this more on the next slide, is that the effect of lighter alloying components, as was discussed a little bit yesterday, is still unclear. They'll certainly lower the values. By how much is not entirely clear. And I have to say, these are very difficult calculations. They're very time-consuming. You're evaluating how electrons interact with vibrations, with how they interact with other electrons. You're solving some very, very difficult and demanding computational problems in these types of simulations. What I would say is that the accuracy of this type of theory for transport properties at really extreme conditions, I would say it hasn't really been demonstrated. That's partly not a statement on the theory per se. It's partly a statement on the failure of the experiments to access this PT regime successfully. So there really isn't the data set that would validate these or invalidate them. So that's not necessarily a shot at theory. It's a partial shot at experiments. Okay, de Coker et al. Have looked at the effect of impurities on the thermal and electrical conductivity of iron. And here they've flipped around. This is actually resistivity, so this is 1 over the conductivity. Sorry. So on this, iron is in gray, so this is the highest conductivity, lowest resistivity. And then as you go up, you get progressively lower conductivities associated with different lighter alloying components. So you can actually drop the thermal conductivity by a fairly decent amount, factor of 2-ish, maybe more if you put in some lighter alloying constituents like carbon or hydrogen. And again, there is the issue about the accuracy of the theory for transport properties. In this instance, the effect of lighter alloying components becomes all important on the problem. And in this instance, they got geophysical core mantle boundary heat flux estimates, probably a little low, but there are some of these that fit loosely into the general window that one would regard as sort of okay. All right, so I'll close with basically a few take-home messages. So, as with almost all characteristics of physical properties of materials, the transport properties are progressively less and less well known, or known with less and less confidence as you go to higher pressures and temperatures. The caveat on this is that there are lots of mechanisms to simply extrapolate them, but you have to be very careful with the mechanisms of simple extrapolation, because if in fact there are changes in the chemistry of the sample, if there are changes in the defect concentrations in the sample, those simple means of extrapolation could be invalid. But those are routinely used. So there is a message there of skepticism. Be a little skeptical when you see somebody just taking an Arrhenius relation and projecting it to the outer core glibly. Trust but verify. You probably need to know a lot of information. Defect concentration, vacancy abundance, H, minor element concentrations to really extrapolate accurately, especially for chemical diffusion and e-conductivity. These are really, really hard issues, and ultimately, probably the defect chemistry of materials at high pressure and temperature is going to be ultimately a major area of effort in the characterization of transport properties. And finally, I just remind you that these are all tensor properties, and that they potentially can be very anisotropic, and that anisotropy could be as important as things like temperature and pressure and compositional effects on the system. Okay, I'll shut it down there. Any questions? Go to him first.
From seismic observations, we find that the slab broadens from upmantle to the lower mantle, and also the LLSVP has sharp edges, and these phenomena influenced by or explained by change of thermal diffusivity, or in other words, can we use the seismic observations to place some constraints on the thermal diffusivity in the different
I'll answer that in two ways. One of which is I would say that the thickening of the slab is probably, from simulations, largely a consequence of the shift in viscosity associated with the two media. So if, for example, you have a relatively thin slab penetrating into a very viscous mantle, it tends to stack up and get thicker. So that's a viscous phenomena in the system. Where the thermal conductivity can play a role is, let's say you have a slab which thickens from, let's say, a generic 100 kilometers to 200 kilometers. That's sort of a 200, 300 kilometers, depending on what it does at the top of the lower mantle. Then you can potentially look at it and say, how fast does that thickened slab thermally equilibrate as a function of depth within the lower mantle? So I would regard it as a mechanistic issue of thin slab going in, encountering a rheologic boundary, thickening up, and then the question is how fast does it thermally equilibrate at that juncture? And that could provide some level of insight in terms of the thermal equilibration of a very thick slab in the deep mantle. On the other hand, you're getting close to, you're not incredibly cold at that depth. So you're looking at differences between relatively higher temperatures than, a lovely 300 Kelvin slab plunging into the mantle. So that would be sort of my extended answer to that, would be how long does a thermal anomaly of X dimensions take to equilibrate in the lower mantle? So that would be where I would go. But my guess is that the answer you'll get will be 5 watts per meter K or something like that, give or take a little bit, or 3 watts per meter K, because it is a fairly coarse thing. And remember, the numbers that we're talking about here are not so hugely variable that when you put them into the square root of kappa t, or square root of kappa t, that the square root of them is going to change things dramatically. So it's a possibility. I'm going to go, he had a question. Oh, sorry. Let's let a student ask a question.
Yeah, I was just going to point out that one of the problems with the first point there is using an Arrhenius relation is that the activation volume is likely to change with pressure.
I totally agree.
Low pressure measurements of activation volume won't be valid at high pressure.
Enthusiastically agree. Absolutely. The point that Dave is making is that within the Arrhenius equation, you have an activation volume. That activation volume is unequivocally pressure dependent. It's dependent on, how a vacancy might respond to pressure, for example. And in some instances, pressure might squeeze out vacancies even, and the delta V might go, way high, for example. So it's a very fair point. Yeah, and I agree enthusiastically.
Can you comment on the diffusivity of solid versus liquid? Like at the same pressure temperature conditions, if liquid or solid, what would be the change?
Yeah, actually and that is diffusivities tend to go up quite a lot on melting in materials, and simply because the ionic mobility gets much higher. And so there's a suite of numbers out there and some of which are derived from electrical conductivity on the diffusion rate in silicate melts. And certainly there is a dramatic increase on melting. I'm not going to quote a number for you right now, but the literature exists, and it is multiple orders of magnitude for most things on melting. That's for silicate melts. For iron-rich melts, it's probably much smaller if you had an iron-rich melt, simply because all the heat is being carried by electrons. So the electron mobility is not so very different in a chunk of solid iron as it is a chunk of liquid iron. So for ionic liquids, absolutely silicate melts way up. Iron, not so much. That would be my quick response. Jackie, I'll give you the instinct.
2 years ago, Frank Stacy was proposing that the iron conductivity is actually too smaller than the current value.
Mm-hmm.
Is there any merit in this idea compared with opposite increasing by factor 2 theoretical results?
Mm-hmm. Well, what Stacy relied on, as I recall, was basically an extrapolative approach. And I've always been a fan of actually looking at data rather than looking at an extrapolation. And so to the degree that, as I recall, he came in lower even than the B et al. Work, like down here somewhere. And the way that I would look at that is, if data negates your extrapolation is probably not right. Okay?
So great to point out that at the very same time he was advocating the existence of the fifth force.
Yeah, that's a good point. You're meaner than I am. You're much meaner. Yes, he was. And so I would be very judicious about that. Let me put it.
This short-range gravitational effect, which in fact I've experienced in Australia. If you drive down the freeway, a car goes to pass you, as it gets close, it stops, and then parallels you the rest of the way. So there must be a
I'll give one sentence on that. The issue was that he did gravity measurements in mine shafts and thought there was a secular variation in big G from the gravity measurements down the mine shaft. And that turned out not to be quite right.
What's the age of your inner core?
That's my inner core, my personal inner core. You know, I gotta say, if you're asking me personally, I personally, there are starting to, if I believe, the geodynamo simulations, which have a very nicely organized flow that accompanies the genesis of an inner core, and before that, sort of more chaotic flows that aren't so clean. If I believe that, then drum roll, yes. And if I believe in the, I would say growing but nascent indications that there was a substantial magnetic field in the Archean, which are, those are dicey measurements too, and all credit goes to those that make them, because those are tough rocks to do any magnetic measurements on. But if I take those at just face value and say that there is a magnetic field back there, then I would say kind of old. I like the idea of a 3.5 billion year old, 4 billion year old, 3.5, 3.2. Give me something like that. That would be my gut preference if you are asking my personal opinion. That is my personal opinion.
Dave Stevenson will be again back in that seat tomorrow. He's just absent today, I know that. He would say you would not need an inner core to generate a magnetic field, but you want to add that to your statement.
Yeah, I know. And it depends on the magnetic modeler that you speak with. I'll take Gary Glatzmeyer's name in vain, because he's right downstairs from me. And say that he would be a little less strong on that point. Let me put it that way. I think that there's a more confused picture that emerges. Certainly in terms of, and the argument would also go back to what the ultimate strength of the magnetic field is, which, the strength of the field in the Archean is going from just field, yes, no, back to how strong is field in Archean. But if it is a respectable field in the Archean, it's a lot easier to generate that if you do have an inner core. So, but that does depend on the Archean measurements. And as I say, I wouldn't want to try and get a magnetic measurement out of those rocks. But more power to those that do. More power to them. It's a pivotal data set.
Wrong with this, but don't the inner core students
This is a good question. Well, and that also raises the question of, are there Archean reversals?
That's the question.
Yeah, I mean, reversals, I think, are, if you have no inner core, my understanding is that you get substantially more waggling of the field that takes place. And so, can you get something that looks north or looks south in a inner core free core? Maybe. I'm not prepared to say that negates the presence or absence of an inner core. But now we've gone from just detecting a magnetic field in Archean rocks to getting its strength to detecting reversals as well. And oh, geez, that's asking a lot of Archean rocks to be faithful recorders of all those things. I had a question somewhere over in here. Yeah, Doug.
Oh yeah, I just want to ask, in your opinion, how important is it to use the temperature and pressure dependent conductivity in the mantle? This seems to be the subject of a lot of argument, whether it's important enough. That it needs to be appropriate.
Well, I guess my gut level take would be, and it's going to be a slightly, I don't want to be glib or cynical, but the adiabats in the lower mantle, for example, is pretty flat. So, loosely, pick a good number, and you're probably okay. Because there's not going to be for the temperature dependent part, because there's not going to be an enormous change. Even if it scales as 1/T, there's not going to be an enormous change between along the adiabat through the lower mantle. Pressure effects, I suspect you probably want to include them a little bit. You probably don't want to make a strictly isothermal conductivity mantle. But it depends on the sort of detail. If you're asking about doing a simulation, a fluid dynamic simulation, will it make much difference? I suspect probably not that much. That would be my suspicion.
So it's secondary to viscosity.
Yeah, very much so. Very much so. Absolutely. Go over there.
Perovskite, you showed this sheeted structure.
Yeah.
There were those calculations for anisotropic diffusion, but what about thermal or electrical conductivity?
Yeah. Entirely unknown. But I mean, certainly you can look at it and go, yeah, all right, if I'm looking at this, depending on the degree to which heat is transported by ionic diffusivity, there's going to be an anisotropy in the thermal conductivity. That's almost absolute. And there will be an anisotropy as well in the electrical conductivity too. I mean, that's just, if you get a structure that's that layered, you're...
Why do they measure viscosity instead of thermal conductivity? It seems like that's a harder thing to measure.
Oh, okay. Well, in terms of calculations, what they're doing is basically the thing that they're calculating is the diffusivity, and then inverting that diffusivity using the Nabarro-Herring equation to get the viscosity. And then they say, hallelujah, we got the viscosity. Look at that, 10 orders of magnitude different. I want to say, eat that, geodynamicist. But that's a big viscosity variation laterally versus this way. So, there's a certain shock value attached to that, which I don't want to underestimate. That's a big variation right there. Colossal. It's incredible. Maybe it's even right. I don't know, but it's very startling. Let me put it that way. Exactly. Excellent question. This is something they danced around very carefully. Or there's a very so what they're doing here is they're essentially saying that you have low viscosity up top, and then that in turn imposes a preferred orientation on the stuff underneath because of the viscous anisotropy of the system. Now you're right. It's a good question that is actually not really very well dealt with, which is that normally you anticipate that materials deforming in the diffusive regime will converge towards isotropy. So what they're doing, as near as I can tell, and this was an excellent question about the paper, this particular paper, is that they're imposing an ongoing stress field on the system that continues to align it while you're getting viscous deformation of the material. So it's at some level of dynamic feedback here, as near as I can tell. That's a very good question, very, very good question as to how this is running. It is not very explicitly dealt with in this work, let me put it that way. Okay, good, you're sick of me.
I think it's time for the break.
Fabulous.